Yeah, we're going to evaluate these definite integrals, but we have to use U-substitution. And we should be already able to do this. It's very simple. You might not have had any homework problems on it, but it's a concept you should know that if you're trying to find the area under a curve, you can just find the change in the antiderivative. Find the antiderivative. Is there a plus c? Sure, but I don't care. I'm going to find the change in it. C's will go away. Okay, we just got f of b minus f of a. So here, I just want to find the change in the antiderivative. The only way I can find the antiderivative, though, is using U-substitution. So I set u equal to the inside of the composition. I go ahead and go through the entire process, solving for dx. Now, I'm going to just write my integral right now. I'm not going to put anything down in my integral, but I got root u, which replaces the x squared plus 2, and dx is going to be replaced by 1 over 2x du. We know that the x's will cancel. It leaves 1/2 root u. I'll find the antiderivative would be u to the 3/2 times 2/3, which ends up being 1/3 u to the 3/2 plus c, but whatever, let's just plug in what u is. It's x squared plus 2 to the 3/2 plus c. We don't need the c's because I'm finding the change between 0 and 2. Now these answers are not nice, but they are the answers nonetheless. I plug in 2, I get 4 plus 2, which is 6 to the 3/2 times a third. And then I plug in 0, I get minus 1/3, 2 to the 3/2. Right? That's fine. Perfect. That's the correct answer. We can check using our calculator. However, there's an alternate way to do this. And it deals with the fact that I did not write 0 and 2 down here. Let me use green. I did not put 0 and 2 here. And I did not put 0 and 2 here. Why? Because this would be incorrect. If you go from dx to du, x's no longer apply. I need u's. So actually, to correctly write this down, I have 1/2 root u du. I can't put 0 and 2 down. They're an interval for an x-axis, which is, dx, says that I'm having an instantaneous change in x. I'm on an x-axis. 0 and 2 are x's. If I'm using du, I've changed things from an x-axis to a u-axis. It's almost like I kind of shifted the graph so that the functions are going to be equal to each other once I replace things. Now, how am I going to put a u here and a u here? Well, we've already established the connection between x's and u's right here. We will use what u is equal to, typically the g of x. So what's going to go here? Well, when x was 2, that means u will just be 2 squared plus 2. That is 6. I'm going to put a 6 here. Where did I get that from? U equals x squared plus 2. Well, down here, when x was 0, u is equal to 0 squared plus 2, which is 2. So I'm going to put a 2 down here. This would be correct. Now watch what happens. I actually could take the antiderivative and find the change between that 2 and that 6. And without having to substitute back the x's, I can get this very same answer, right? 1/3 6 to the 3/2 minus 1/3 2 to the 3/2. So this is like an alternate way to find this area under a curve. Just use u's, and instead of changing back to x's, instead just change your interval to u's. Okay? Why don't you go ahead and try that with this one, finding this area using u's. I'm going to change it a little bit. We have 2x, x squared. Let's go with minus 1 squared. Okay, U-substitution. We'll set u equal to the inside of our composition. Take the derivative, solve for dx, substitute in. But once we substitute in u's, change your interval. Instead of from 0 to 2, change it to a u to another u. Okay? So this is good. We got 28/3. That's the correct answer. And I didn't have to switch back to x's. Now you're probably saying, but like, why do that? Why not just switch back to x's and just go 1/3 x squared minus 1 cubed from 0 to 2? Well, you're going to get the same answer anyways. It's just like, when do you want to do the work of plugging in your value into what u is equal to? Do you want to do it early on? Well, then just use u's and you get the same answer. Do you want to do it later? Plug in 2, you get 4 minus 1, that's 3. Plug in 0, you get 0 squared minus 1. It's really just the same thing. It's just whether you want to do it earlier and later. Most of you will probably just go straight to here, skip this to get that. And that's fine, except for questions that require you to do this whole change of the interval. Okay? A question like this. We have an integral from 4 to 9 of f of 2x dx, which is equal to 6. Notice that it's equal to a value. Keep that in mind. What would be the equivalent definite integral using f of u instead of f of 2x? So your goal for this question is not to figure out what this is. It's impossible. But to fill in what goes there, in an integral of f of u du, which is equal to some other missing number. Now, I just want f of u du, nothing else in that integral. Now, for questions like this, students sometimes totally forget the whole process that they use for U-substitution. And they just start replacing u, but not doing all the other details involved when we're doing U-substitution. You can assume that u is equal to 2x, and that would be correct. Don't just substitute in u, right? You have to substitute in u, you have to substitute for dx. So I'm still going to take the derivative like normal. I'm still going to solve for dx, substitute that in. The only difference here is that this answer here, I want nothing else besides f of u du. Okay? Go ahead and see if you can figure it out. Check your answer with a neighbor. Check your answer with a neighbor. We have 18. Everybody should be getting that. But I have f of u times 1/2 du equals 6. I'd want nothing else besides f of u du in the integral. I know this is 8 and 18, so at least I got these two pieces correct. What can I do with that 1/2? Good. You can pull out this 1/2. It's a property of an integral that a constant can be pulled out, just a constant. Then multiply both sides by 2, and this becomes a 12. Okay? And there's your answer. Let's do another question similar to this question. I'm giving you what u is equal to. I'm giving you an integral from 1 to 4 of, this is an e to the root x over root x, and I want you to rewrite that integral using just u's. No x's. Okay, I'm going to work with you, and then we'll get to a spot and see if you can figure it out. Okay, we're told what u is equal to, so we'll go ahead and take the derivative of that u. I get du equals 1/2 x to the negative 1/2 dx. I'm going to rewrite that as 1 over 2 root x. It's very, very important to do that. That will help you see the things that you can cancel by getting rid of that negative 1/2. To solve for dx, I'll multiply both sides by 2 root x. And I get that. All right, so I will substitute in U. Well, it'll go for this root x, and it looks like it'll go for this root x. I will substitute in what dx is equal to. I have 2 root x du. It's a little crowded. I can change my interval. Make sure you do that. And I'm going to have to figure out what I can do with this root x and the u. Because this seems like a problem. I want u's and no x's, but I have an x and a u. See if you can figure that out and also change your interval. The interval should be the easy part, right? You know what x is? You can use your relationship between the u's and x's. So we should at minimum get from 1 to 2. But what do I do with that root x? Zoe? We already said what root x is equal to. It's equal to u. Well, that means this u can cancel with that u. And all of a sudden we have 1 to 2 of 2e to the u. Okay? Well, now, that brings us to the next question. Could we evaluate this? Do we know the antiderivative of 2e to the u? Or think about it as the antiderivative of 2e to the x. Who can tell me what the antiderivative of e to the x is? E to the x. Let's remember that the derivative of e to the x is a perfect segue, is e to the x. Don't worry about this. Well, that means the antiderivative of e to the x is e to the x. Or if you have e to the u, guess what? It's e to the u plus c. Don't treat it any different than just another variable. Okay? Now, this is where things sometimes crisscross wires in students' brains, and they get all messed up if they haven't been all messed up already. Because the antiderivative of 2e to the u is 2e to the u. From 1 to 2 would be 2e squared minus 2e. Right? Well, Mr. Messner, didn't you just take 2 and plug it in here and take 1 and plugged it in there? No, didn't do that. I took the antiderivative first. Okay? Don't just plug in those numbers from that integral into what's inside of it. That doesn't work. It doesn't work. I took the antiderivative. This is the antiderivative of 2e to the u. Okay? Let's go back up to that first problem. Don't just take 2 and plug it in there and take 0 and plug it in there. Okay? You're taking the antiderivative. Now, for ease, it happens to stay the same, but you've still taken the antiderivative. Okay? Okay. Now, if I have something like a constant in front of the x, say e to the 3x, what do you think that antiderivative is? Would it be 3 to the 3x or 1/3 to the 3x? I heard both of those answers at the same time. Let's recall the derivative of e to the 3x would be 3e to the 3x. The derivative of e to the 3x would be e to the 3x times 3. So I need the reciprocal of the coefficient of x in front of that e to the 3x. If I have something like e to the 4x plus 1. Guess what that antiderivative is going to be? Yes, just the reciprocal of the coefficients of x in that power plus c. So this is the whole getting around using U-substitution because we just have a coefficient of x. If I have e to the kx plus anything, as long as it's not another x to a power, this antiderivative would be 1 over k e to the kx plus whatever else it has, as long as it's a number. Okay? So that's like antiderivative of cos 3x. It's 1/3 sine 3x, right? But sometimes it's not that easy. Sometimes you'll have something that looks like this. Oops. If I see something being multiplied by e to a power, and I notice that the derivative of the power is a version of whatever's being multiplied by e to the power, I should be thinking U-substitution, set u equal to the power of e, typically. That is the composition. That's e to the power. The power is the composition. Now, this is typically, not always. Okay, so let's see what we get. We get u is equal to negative x squared. Du is equal to negative 2x dx. Dx is equal to negative 1 over 2x du. Sub in u, sub 4 dx, cancel some things, take the antiderivative, hooray. Negative 5/2 e to the u is what I have. Its antiderivative would be negative 5/2 e to the u, which is negative 5/2 e to the negative x squared plus c. Bringing us to another one just like that, this one right here on the left. Go ahead and try that yourself. Well, let's tackle this one down here. What should I do? If I set u equal to x, I'll just get du equals dx. Nothing cancels. I just have 1 over e to the u du. Other ideas for 1 over e to the x? Mr. Chris Stockton? Ah, good idea. Let's rewrite this as e to the negative x. Now, to take this antiderivative, guess what? It's just that kx, k is negative 1. You'll have, 1 over k, or just negative e to the negative x. Turns out the derivative of e to the negative x is the same as the antiderivative of e to the negative x. Okay? Now that actually brings me to a question that I have. What's the antiderivative of 1 over x? Because I'm thinking if I have e to the negative x, it's starting from 1 over e to the x. Looks like I need to rewrite this as x to the negative first, right? Same idea. And it looks like I'm going to use the power rule for this. Well, go ahead and use the power rule to find the antiderivative of x to the negative first. Well, I add 1, I get x to the 0, right? So that means it's got to be 1, right? Must be. But no, that doesn't make sense because the derivative of 1 is definitely not 1 over x. Okay, well, I guess I did forget to multiply by the reciprocal. We can consider the reciprocal of 0 as like 1 over 0. So maybe this antiderivative just does not exist. Well, that's not right either. Turns out the power rule works for every single exponent of x except for 1, negative 1. The power rule does not work for 1 over x. Okay? We need to recall the function whose derivative is 1 over x. Now, was it Miss Dietza or Miss Ali? It was you, Miss Dietza. Miss Dietza, which function's derivative is 1 over x? Yes, log function. The derivative of the log function is 1 over x, which means the antiderivative of 1 over x is log x. This is super important. We try to use the power rule for all these x to powers, but not for 1 over x. Okay? And we think it'd be that simple, but it's not. Because when I start with log x, I start with a function that is only defined for positive numbers. This is the log function, right? Inverse of e to a power. E to the power grows exponentially quickly. Log x will grow exponentially slowly. E to the x is never negative. Log x, you can never plug in a negative value into it. Okay? Inverses. So that means that since log x is just greater than 0, 1 over x would be its derivative, its tangent slope generator, when x's are greater than 0. This function right here is 1 over x when x is greater than 0. And if you look at the tangent slopes of log x, you see the values of 1 over x when x is greater than 0. So yes, this is true. The antiderivative of 1 over x is log x, but just for when x is greater than 0. But if I start with what is the antiderivative of 1 over x, if this is my beginning, maybe I'll move this over to the left side and replace it here. So it's like this is number 1. Well, 1 over x is defined for all x values except for 0. So now I have the full graph of 1 over x. Okay? Well, I need, the accumulated area function that will give me, the graph of 1 over x. I need the antiderivative. What ends up happening is log x isn't going to work because we're only over here. I'm going to need another piece of a function that'll look like this. And what that function is not just log x, but the log of the absolute value of x. Now, we are talking about any value except for 0 for 1 over x. So if we start here with what's the antiderivative of 1 over x, we need to add on a domain for log x by using this absolute value. Which means if I asked you what the derivative of log absolute x is, you'd say it would be the entire graph of 1 over x. Sorry, no plus c there. Okay. Now, if you have the antiderivative of 1 over u, guess what? It's just going to be log absolute u. Treat it just as a different variable, not differently from x. Okay? Now, recall the chain rule with the log function. If I have the log of 3x cubed plus 2, its derivative was 1 over 3x cubed plus 2 times the derivative of that 3x cubed plus 2. So this is the chain rule. Well, if I have functions like these, 1 over 4x minus 1, or 1 over 5 minus x, let's see if we can get the antiderivative of something that looks like this. We could use U-Substitution here. I don't think it's necessary. What do we think the antiderivative of 1 over 4x minus 1 is? The log of 4x minus 1 would not be correct. Nope, that would not be correct as well. Because remember, if I took the derivative of this, I get 1 over 4x minus 1 times 4. I need the reciprocal of the coefficient of x. Just like I did for e to the 4x, just like I do for the sine of 3x, if you're taking the antiderivative, you need the reciprocal. I don't know why I put a k there. You need the reciprocal of the coefficient of x. Which means for this guy, it's not just log absolute 5 minus x. It's negative log absolute 5 minus x. Which means if I want to take the antiderivative of something like this, I can always say it's 1 over k, log absolute, kx plus whatever. But there's another way. And the other way comes from this example in the top left. What could I do that would maybe be a step 0, the simplify step, to take the antiderivative of 3 over 5x? Nope, I wouldn't want to write it as x to the negative first. That does not help me. I would prefer to rewrite it as this. And all of a sudden, I say, okay, it's a constant. I can pull the constant out. Antiderivative of 1 over x log absolute x, 3/5 log absolute x plus c. Well, that actually gives me an idea for another way that I could tackle something like this guy right here. Who's got an idea of what I could do similar to what I did before on the 3 over 5x to take this antiderivative a different way to give me a different answer, but still correct? Discuss that with maybe a neighbor. Throw around some ideas. Area. What do you think, Mr. Johnson? So you would think you could say 1 over 4, and then you'd have x minus 1. Is that correct? I have to divide everything by 4 if I factor out this 4. So this would have to be x minus a fourth. Now, all of a sudden, I actually can write this antiderivative as 1/4 log absolute x minus 1/4 plus c, which is different from this. However, logs work in mysterious ways. These are actually functions that are shifted up or down. So their derivatives will be the exact same. The derivatives of this will be 1 over 4x minus 1. The derivatives of this will be 1 over 4x minus 1. But two answers that appear to be different answers, but are both correct. Now, this will blow your brain. This is multiple ways to do the same thing. I know you guys hate that. I usually do this. Usually on like answer keys to things, you'll see that method. Okay, but this is totally okay. So whatever you like to do, go ahead and do, and feel confident that you're doing it the correct way. Okay? What do you like, the top or the bottom? This be in? The top. Okay, then stick with the top. It's fine. Well, those are the easy ones. There will be some, and you just have to recognize this, where the numerator of a fraction is the derivative or a version of the derivative of the denominator. Notice this fraction, x over x squared plus 1. You cannot simplify this. You cannot put x over the both of them. You can't do that. It's not allowed with fractions. So we got to think and we got to see that x is a version of the denominator derivative, derivative of the denominator. I take the derivative of x squared plus 1, I get 2x. That's going to enable me to cancel that x and use U-Substitution. Okay, let me show you. Set u equal to x squared plus 1. Go ahead and do the steps that you normally do. You have 1/2 times 1 over u du. The antiderivative of 1 over u would be log absolute u. So this would be 1/2 log absolute u plus c, or 1/2 log absolute x squared plus 1 plus c. Okay? If you see this, you should notice the derivative of the denominator is the numerator, set u equal to the denominator. We're going to skip that. But we will do this. The antiderivative of tangent. We don't even know what that is. We don't know whose function's derivative is tangent. But I have the tools now to find the antiderivative of tangent. It starts by rewriting it as sine x over cosine x and recognizing that the derivative of your denominator is a version of your numerator. Go ahead and set u equal to your denominator and find the antiderivative of tangent of x. We end up with something that is not so simple as we thought it would be, but it is the antiderivative of tangent. It would be negative log cosine x. Not something you would have to memorize, not even something that you'd have to do on a test actually, but it is a good example of what you can do. All right, that's it. This game is so easy.